So the next talk is by Alex. He's at MIT, and he's talking about complexity-guided data sampling for training neural surrogates of programs.
All right, everyone hear me? Okay, make sure my clicker does not seem to be working. All right, whatever. So, hi everyone, I'm Alex. I'm going to be talking about our paper, Turaco, Complexity-Guided Data Sampling for Training Neural Surrogates of Programs. This is co-authored with Yi Ding and my advisor, Mike Carbin. Let me start by defining a surrogate of a program. So a surrogate is a model of the behavior of a given program. And this is typically something like a neural network, which you train such that for any given program input, it predicts what the program would produce as output for that input. People like surrogates because surrogates can help to improve the speed and the accuracy of programs. And I can ground this in some examples from the literature. So in some prior work, Ismail Zadeh and co-authors trained surrogates of numerical programs to speed up these programs at the cost of a little bit of approximation error. And by training these surrogates to mimic the program and deploying them in their place, they were able to find surrogates that were about 2 to 3 times faster than the original programs. Kutzkowski and co-authors trained surrogates of physics simulations and then fine-tuned these neural network-based surrogates on some data from the expected actual behavior of the process that the simulation was modeling to increase the accuracy of the surrogate relative to the simulation. And by doing this, they were able to find surrogates that were about 2 to 3 times more accurate than the original simulation. And in some of our prior work, we trained surrogates of CPU simulators and then exploited the fact that these neural network-based surrogates are themselves differentiable to optimize simulation parameters of the original simulation against the surrogate, ultimately finding simulation parameters that actually increase the accuracy of the original simulation relative to expert set parameters or values for those parameters. So as you can see, there's a wide range of applications of surrogates of programs, and each with potentially substantial benefits. And the first step of each of these different design patterns involves actually training a surrogate, a neural network-based surrogate, to mimic the behavior of a given program. And this raises the natural question, what is the methodology for doing this to get the best accuracy surrogate if you know the source code of the original program? And in this work, we focus on one particular aspect of this question, which is what data distribution should you use to train a neural network-based surrogate of some given program? So I will make this more concrete with a case study from our paper. And so specifically, this case study is going to be of a 3D renderer program, such as from a video game engine, that will generate this scene here. And we're going to be looking at creating a surrogate of one particular tiny sub-program of this overall renderer, which is going to be this luminance shader here. So this is a shader program a shader that is essentially executed for each different point in the input scene, thousands of times to generate each frame of the render that I was just showing. And so it takes 2 inputs. It takes the sun position, which is the Y position of the sun in the sky, ranging from -1 at night to +1 during the day, and the emission properties of the material at that point in the scene, whether it's absorbing light or reflecting light. And then as output, this predicts the luminance of that point, which is the amount of light reflected from that. So if you look at this program, you might notice that this program essentially divides up the input space into 3 logical regions and then applies a different function to each of these different regions of the input space. So there is the nighttime path when the sun position is less than 0, and this ends up computing this relatively simple linear function of the input variables. There is the twilight path when the sun position is between 0 and 0.1, which computes a maybe slightly more complicated but still ultimately linear function of these input variables. And then there's the daytime path, when the sun position is greater than 0.1, which computes this much more complex, actually quadratic function of these input variables. And this leads me to the key insight of our work, which is essentially that when we're training surrogates of programs and we're trying to reason about how much data to sample from each different region of the program, we should be using the sample complexity of the function applied by the program to these different regions to guide how much data we are sampling from the program. And so for anyone not familiar with the term, sample complexity is essentially the number of samples that are required to learn a surrogate of a given function to some target error. So essentially, the higher the sample complexity, the more samples you need to learn a reasonable surrogate. And we can empirically look at the sample complexity of each of these different program paths. So I have a plot here of basically training a surrogate of each of these different paths in isolation and looking at the error as a function of the amount of data used to train that surrogate. So in this plot, error is on the y-axis, the data set size to train a surrogate is on the x-axis, and each different line is a surrogate of each of these different paths. And so you can see, essentially, the empirical sample complexity results match the intuition that I was trying to lay out earlier about the complexity of each of these different paths, right? So for a given number of data set samples, the nighttime path, which is the simplest linear function, has the lowest error, whereas the daytime path, which is a more complex quadratic function, has the highest error. And so essentially, we can use this notion of the complexity of each of these paths to help us determine how much data we want to sample overall from each of these different regions in the input space to guide, or yeah, to train our surrogate of our program. And so we want to compute these sampling ratios. And this will have two different ingredients in the recipe. The first is the complexity, which was I was just laying out earlier, right? The nighttime path has the lowest complexity. I'll quantify this in a little bit. And the daytime path has the highest complexity. The other ingredient here, of course, is going to be the frequency of each of these different regions in a workload of interest. And so if we assume that the sun position is uniform from -1 to 1, then we get that the nighttime path is induced by about half of the inputs. The twilight path, which is relatively rare, is induced by 10%, and the daytime path by 40%. And so this can guide some really high-level reasoning about how much data we might want to sample from each of these paths, right? Because the nighttime path is by far the easiest of, the simplest of these, has the lowest complexity, we should probably be sampling less than its frequency to train a surrogate. Whereas because the daytime path has the highest complexity, we should probably be oversampling it relative to its frequency. And this leads me to the second key inside of this paper, which is that when we are training surrogates of programs, we actually have access to the source code, the semantics. We know the exact function that we are trying to train a surrogate of. And so we can use tools from machine learning theory to actually exactly compute the sample complexity of the function, each of these different functions, and then use that to determine exactly how much data we actually should be sampling from each different region of the input space. And so using an approach that I will describe in just a minute, we can essentially compute that the sample complexity of the daytime path is actually 3.7 times that of the nighttime path, so it's significantly more complex to learn a surrogate of. And then using another approach I'll talk about in a minute, we can then compute these actual sampling ratios concretely. So we can get that we want to sample roughly 40% of our data from this nighttime path, so undersampling relative to the 50% frequency, and 46% from the daytime path, oversampling relative to its frequency. So how well does this approach work? I have another one of these plots with the dataset budget on the x-axis and the error on the y-axis, comparing training a surrogate of this program according to just the frequency distribution in green and the complexity-guided sampling ratios in orange. And so this is a log-log plot. It's actually a little bit hard to see exactly the gap between this, but on this range of dataset sizes evaluated here, you get about a 15% improvement in error by training according to these complexity-guided sampling ratios compared to just training according to these frequencies alone. So this is a pretty significant improvement in error in this example. So we have two core contributions in our paper. The first is this high-level approach to allocating samples to different regions of a function's input space to train the highest accuracy surrogate, based on each region's relative frequency and complexity. And this approach essentially follows the intuition I was just laying out. Regions that are more frequent, we want to sample more. Regions that are more complex, that are harder to learn, we also want to sample more. And our second contribution is Turaco, which is a programming language in which we can actually compute the complexity of the function applied by a program to each different region of its input space. And so together, these two contributions allow us to reason about the data distribution to use to train the highest accuracy surrogate of some given Turaco program. So I've laid out a lot of the intuition. Let me lay out some of the actual formal foundations behind our approach. So the core modeling assumption that we have to make is that the programs under study denote these stratified functions. These are piecewise functions. Essentially, we assume that the program applies a different function to each different region of the input space. And to learn a surrogate of such a stratified function, we learn a stratified surrogate, which is itself, a piecewise surrogate. So we learn each surrogate of each different function stratum independently. And then at evaluation time for one of these stratified surrogates, we essentially determine what input or what region of the input space a given program input lies in, and then apply the corresponding surrogate. To train the best, surrogate of a given function, we have to actually be able to reason about the error of a surrogate of a given function as a function of its complexity and the amount of data available. And as I mentioned earlier, to do this, we use this notion of a sample complexity measure, zeta of f. And so, as I said earlier, the error of a surrogate of f at a given number of samples is proportional to zeta of f. So the higher this complexity is, the more data you need to learn a surrogate. What are these sample complexity measures? I've used them sort of informally, but I haven't actually talked about concretely what they are. we can actually take advantage of some recent work from the theoretical machine learning community to compute these sample complexity measures for certain classes of functions. So we can actually know exactly, or an upper bound at least, on the amount of data for certain class of functions to train a neural network to mimic that. And so the core assumption that these approaches from the theoretical machine learning community, which we actually inherit in this work, is that the functions under study are themselves analytic, which means that essentially that they have this type of power series representation. To compute this zeta of f for an analytic function, we have first, as a utility, define the tilde of a given function. And so this is essentially the power series representation of this function with all coefficients taken the absolute value of. And so essentially you can think of this tilde as a way of measuring the influence of the sort of hard to model for a neural network, higher order terms of this power series. Then these results from the theoretical machine learning community actually tell us that zeta of f, the complexity of f, is equal to the derivative of the tilde evaluated at 1 squared. And so there's a lot of assumptions baked into this about the neural network architecture and data, but essentially this is the sample complexity for an analytic function. And so just to plug this back into the definition of sample complexity, concretely, the error of a surrogate, epsilon, is upper bounded by the square root of zeta of f over n. So the higher the complexity is, the higher the error is. The more samples you have, the lower the error is. So just to sort of formally state, or a little bit more formally state, our optimization problem here, we assume we are given a stratified analytic function. We assume we are given a data distribution that describes the frequency of each different region of the input space in a test workload of interest. And we assume we're given an overall sample budget. And our goal is to find the allocation of the sample budget to different strata to minimize the overall error of the stratified surrogate against our original function. And we do formalize this in the paper. I'm not going to have time to go into this formalization, but as I've laid out, essentially the intuition is that we want to sample proportionally to the frequency of each different region and the complexity of each different region. Okay, so how do we actually compute these complexities for programs? So to do this, we introduced a programming language and associated analysis, Turaco. And so in Turaco, all programs are stratified analytic functions. So it's this imp-like programming language that looks essentially something like this. And so our goal in our Turaco analysis is going to be to compute zeta of f, this complexity measure for each different region of the input space, or the function applied to each different region of the input space. And our analysis has two components. The first one, which is sort of the interesting novel bit, is this non-standard interpretation to calculate the tilde of f. And so I'll quickly walk you through how this analysis, this interpretation works. So I've duplicated the definition of the tilde of f here. So it's the power series representation with all coefficients taken the absolute value of. So let's say that we have a program that computes just something simple like f of x equals sine of x. We can write out its power series representation like this. And then so if we want to compute the tilde of f, we want to write out this power series representation with all coefficients taken the absolute value of, which is equal to sinh of x. So essentially the tilde of f of x and sine of x is just sinh of x. And this is essentially how this analysis operates. We are able to replace each different operation with the language with the tilde version of the operation, and then the actual analysis of the tilde itself is compositional in these operators. So we just do this sort of non-standard analysis to compute the overall tilde. We combine this with a standard forward mode AD pass to compute the derivative of the tilde, and then by evaluating this at 1, we're able to then have this automated approach for actually computing the complexity of a given program. So we have this zeta of f for a program in Turaco. Let me walk you through a little bit of the evaluation of how we evaluated how well these complexity-guided sampling ratios work. So I talked a little bit about this example of a luminance shader from earlier, in which we got about a 15% improvement in error relative to some baseline distributions. We evaluate this on a range of other programs and get an average of about a 5% improvement in accuracy of this complexity-guided sampling ratio relative to baseline approaches. And so 5% probably doesn't sound like a lot to people in this room, but I want to talk you through what this means in the machine learning context, because a 5% improvement in error can actually make a real difference in sort of endstream or downstream applications. So in some prior work, we were developing a surrogate of a program to try to have the fastest possible approximation of this program that had no more than a 10% additional error compared to the original program. And to do this, we performed this hyperparameter search on the size of the neural network. And so we ended up selecting a neural network width of 64, which had about a 57 or 1.57 times speed up compared to our original program. With a 5% reduction in error, though, we're then able to actually redo this hyperparameter search and select a significantly smaller neural network architecture with about half the width, which has an additional about 28% speed up. So a 5% reduction in error actually can lead to significant improvements in the downstream performance of the application. I also want to very briefly touch on some sort of qualitative analysis of these results. So I talked about the renderer program that we evaluated earlier. And so we ended up training a surrogate of a much larger component of this program than just this sort of simple luminance shader, and evaluated our our surrogate trained according to these complexity-guided sampling distributions to several baselines. And so on the left here is going to be the original sort of ground truth render. Then the three other figures are the renders generated by a couple of different surrogates. On the left is the complexity-guided one, which is the closest to the ground truth. In the middle is a render from a surrogate trained on just the frequency of these distributions of paths. So it's also quite similar to the ground truth, a little bit hard to see it in this projector, but the nighttime is significantly more purple than the original ground truth is. You can see it sort of on the roof of the building. And then the rightmost is a surrogate trained according to just a sort of uniform sampling distribution across paths, which you can see is nowhere near the actual ground truth render. Just to very briefly recap, surrogate to programs are this emerging design pattern, an emerging programming technique that allow us to improve the speed and the accuracy of programs by replacing them with surrogate models of their behavior. And when we're training surrogate to programs, this is sort of this interesting machine learning task where we actually have access to the source code, the semantics of the program. We know exactly the function that we're trying to train a surrogate of. And we argue essentially that we should be able to use this knowledge and combine this with our both theoretical and our empirical knowledge of machine learning to be able to train the best possible accuracy surrogates of programs, or broadly the best for our downstream application, based on some analysis of facts derived from the original program. So thanks everyone, and I'm happy to take any questions now.
Right, so we have time for one very quick question.
Hi, thanks. Wonderful talk. I think lots of interesting ideas. Quick one, how do you deal with programs that have loops? So the analytical functions would be infinitely many in the representation.
Yeah, so our approach supports bounded loops, and essentially what this will look like is that you have many, 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 many different strata. And so it realistically does not scale super well to that, because we assume that currently we train essentially a different surrogate for each stratum.
Another question. This was a very quick one. Thank you for that.
Hi, thank you for the great talk. So I was wondering, you compute like based on the sample complexity, how many samples or like a ratio of samples that you need to take. Is there any instance where you don't even have the necessary samples in your training data set to match that, and you can't actually learn a surrogate program? Because you have a finite data set, and some of these functions could be quite complex.
Yeah, so ultimately our approach gives essentially the best allocation of samples that you can given your sample budget. And so if your sample budget is not large enough, I mean, you will learn a surrogate. It will probably be terrible. But yeah, so there's never a case where like it won't learn anything. It'll try to learn the best given the sample budget. But if it's small, there may be issues. And especially you can run into issues where the approach, essentially you have to round to integer numbers of samples and things like that, right? And so you can end up with kind of these weird edge cases in the really, really small data regime.
All right, let's thank Alec again. And
All right, thank you.